Elkem produces various ferrosilicon alloys for the foundry industry. A key element is the post-taphole processing of liquid metal. Here, the correct chemistry and temperature is obtained prior to solidification of the alloy. Post-taphole is divided into three sub-processes, as depicted on the schematics: tapping, refining/alloying, and casting. During the COGNITWIN project, Elkem, in cooperation with Cybernetica and Syntef, have worked to improve the decision support that the operators use to ensure that the product specifications can be met. The strategy has been to combine infrared camera technology and image analysis together with a mathematical model developed by Cybernetica. Infrared camera technology has improved our ability to provide more information about the process, related both to the accuracy and frequency of which a particular process parameter can be estimated. The output from infrared cameras combined with image analysis can be summarized as follows. For tapping, a continuous temperature measurement is done together with a quantification of the amount of slag following the metal from the furnace. In the refining alloying stage, the infrared camera gives a continuous temperature measurement as well as slag coverage measurements, both of which are essential to monitor the heat loss during metal processing. In the casting stage, the slag amount during casting can be measured. All of these parameters can now be provided to the online mass energy model that will ensure optimal processing of the liquid ferroalloy, both in terms of maximizing the yield and ensuring proper quality of the finished product. A direct view of the tapping hole of a ferrosilicon furnace is usually obstructed by large amounts of smoke, hot gases, and extremely bright light from the high temperature metal. As seen from this brief extract from a video stream, the infrared camera allows for easy observation of the metal stream from the tap hole. Elkem has developed algorithms for identifying slag and metal from a video stream as shown here. In the example, slag droplets in the stream are shown in a green color to aid the eye. The main output is the amount of slag measured by kilograms per tap. In addition, the infrared camera gives a continuous temperature measurement that is very useful for understanding the overall furnace operation. During refining and alloying, it is important to be able to estimate and understand heat losses. An important factor is the slag coverage due to the large difference in thermal behavior of a slag phase versus the metallic alloy. An insulating layer of slag will have great effect on the rate of which energy is lost from the molten metal, as the main contributor is radiation from the surface. Being able to monitor this in real time is a huge improvement, and parameters such as slag coverage and temperature can now be provided to the online model for a more accurate calculation of the heat mass balance of the batch. The last infrared camera monitors the casting process. As metal is poured from the ladle through a runner and into a moving casting belt, image analysis algorithms detects and measures the amount of slag following the metal from the ladle, if any. This is an important quality indicator as the slag tolerance in the finished product is quite limited. The application of infrared camera technology will greatly enhance our ability to detect slag in the cast product and act before the metal is shipped to the customer.
You have now been introduced to the machine vision algorithms that have been developed for the Elkem pilot. This part of the demonstrator will focus on the operator support system, which presents the results from the cognitive digital twin to the operators. Here you can see the operator support system that is currently running online at the plant. The cognitive digital twin is still being verified, so the operators use the existing control system to calculate the amount of each addition. This graph shows the temperature of the molten metal. The vertical black line indicates the current time with past values to the left and predictions to the right. Information about the batch is shown to the right. Here operators can see the planned addition of each alloying material and the amount of recycled cooling ferrosilicon to use. The optimized additions, calculated by the cognitive digital twin, are shown side by side with the planned additions. The operator can then easily compare the results from the cognitive digital twin with the existing control system. The cognitive digital twin is set up to minimize the use of alloying materials, while still adhering to the grade specification with respect to concentrations. At the same time, the recycling of cooling ferrosilicon is maximized while adhering to the temperature target for the casting. The temperature graph shows two trajectories. One where the operators follow the planned addition in this dark blue line, and one where the operator follows the optimized additions calculated by the cognitive digital twin. Thereby makes it easy to compare the two trajectories. The cognitive digital twin continuously re-optimizes, thereby taking new additions into the ladle into account. See here, some of the alloying materials have been added according to the planned additions, and the optimizer has adjusted the amount of cooling ferrosilicon accordingly. When the end of treatment is getting close, the optimization is turned off, as it will be too late to take any corrective action. Finally, a temperature measurement is taken, marking the end of the treatment. Once the verification of the cognitive digital twin is complete, it will reduce the use of alloying materials, thereby allowing for an increased recycling of cooling ferrosilicon. This will reduce material and energy consumption while also increasing material yield. Thank you for watching this demonstration.